Welcome back to our second meeting of Architecture for Geographers. As a reminder, we'll be studying architecture through the lens of the Vitruvian ideal, and today we'll begin with the underpinnings of firmness, commodity, and delight. We'll begin with a fairly intensive look into the stresses on building structural members and the forces that create them. While we won't be doing any of the math or engineering equations that we use to design structures, we will explore those principles in a way that will give you, I hope, will give you a physical sense and understanding of how buildings stand up. This is a lot of material to digest at once, so I've meandered off course at one point to enjoy the beauty of structural expressions in one of their purest settings. I love, and I'm pretty sure I speak for all architects, architects love bridges. We'll then take our first structural system, beginning where buildings begin with, foundations, and then segue into our first building material, concrete, the most common material for foundations, but also with a myriad of other applications as well. We'll conclude the first half of today with a fan appreciation of the Pantheon in Rome, a remarkable concrete structure and one of the world's most gorgeous interiors. Then, after a musical intermission celebrating the Pantheon, we'll move on to our first look at the functionality aspects of commodity and look at architectural program with, in the spirit of today, two concrete examples. In 1977, Charles and Ray Eames, the avant-garde thinkers and architects, produced The Powers of Ten, a short film that presents our universe as a series of jumps in scale from micro to macro. And for us, it's a reminder that architects need to consider their design in the context of an order of magnitude or more outside their scope, and then delve deeply into the problem as well. We won't actually watch the film on the slideshow, but we will in class. Our first examination of architectural delight will be of the earliest proportional systems studied by our architect forebears. And then finally, after reviewing last week's assignments and discussing this week's, we'll wrap up with a case study of Joyner Health Science Center, a project of mine for the state of Connecticut, and look at it considering the aspects of the project that relate to our discussions for today. This is a lot to cover, but before we begin, I'm introducing a new game for us, a new geography game of Guess the Sketch. This is a public high school. What city do you think it's in? Trabeated structures, or structures composed of horizontal members, generically called beams, spanning between two vertical supports, are the most basic form and the vast majority of architectural structures, as nobly represented by the Parthenon. When Vitruvius wrote his books on architecture, the Parthenon had already been standing atop the Acropolis for 500 years, demonstrating the structural stability and material longevity expected of a model for firmness. A little bit of nickel knowledge sidetrack here for a minute. I said generically called beams because you will come across numerous terms for beams depending on the situation where they're being used. Common beams that support floors are joists, beams themselves, and then girders in ascending order of strength. In other words, joists frame from walls or into beams. Beams span always from walls or columns, and beams may also span onto girders, which would support beams. Other, esoteric ones are spandrel beams that carry the exterior walls of a building, while rim joists occupy the same position. They're supported by the wall that they're part of and hold the common joist in space. They're not actually acting as beams. Header joists or headers frame across openings in a joisted floor system, most commonly for a stairwell, while lintels are short, independent members that support openings in walls, independent in that they're not tied into the building's floor framing structure. Also, any beams made of stone are often called lintels wherever they are, as are the lintels of the Parthenon, which are bearing on their Doric columns. In later weeks, we'll look at how other structural systems, walls, arches, vaults, trusses work. But today, we're going to study how we size and design the beams and columns of a typical structure. The first and most basic condition we will consider is where a structural member is in compression, which occurs when an axial load is applied to both sides of the member, or where the force is applied from one side and resisted on the other, which is essentially the same thing. In other words, if it's unrestrained on the opposite side, then Newton's first law applies, and, for example, a car rolls forward. Not a good situation typically in buildings. Obviously, then the opposite is if it is resisted and the car runs into a brick wall, Newton's third law applies and the car is in compression. That's what we're looking for in buildings, even though that's not what you're looking for in automobiles. To get a visceral sense of compression, I'd like you to consider what it would feel like doing a push-up, as our athlete model here is doing. Your arm is in compression from the load that your shoulder's applying onto it, and that's what compression feels like. The caryatids that are holding up the temple above them are feeling compression through their whole bodies. The way we design a member to resist compression, a column for example, is that we've taken all the loading from the structure above and determined how much is being distributed to our given column, and that's the load it must resist. Through the course of history, we've empirically studied and determined the minimum compressive strength of all common building materials. Compressive strength is expressed in pounds per square inch. For wood, for instance, it's typically in the thousands of pounds per square inch. Things are very strong in compression. Because materials essentially can bear a given weight per given amount of area of member, it's a very simple equation to determine how big the column needs to be. It's just the load divided by the area. However, the complication comes in that columns will fail in buckling. The way to imagine this is if you've done 50 push-ups, your elbow is going to give out and buckle at the center of the column. Same thing happens with structural columns. So we have to explore what we call the slenderness ratio. The shorter and stouter, the stronger the column will be, the more it resists buckling. A subtle and beautiful example of this is seen in the Doric column from the Parthenon there. The example is where the Greeks swell very slightly the column. It tapers from the bottom to the center and then back up to the top again to express its resistance to buckling. And this is called entasis of the column. It's a subtle and beautiful detail that if it's not there, an architect will notice that the builder didn't know what they were doing typically. It doesn't have the beauty of an actual Doric order. The second basic condition is where an object is pulled in both directions, when the structural member is then in tension. To physically understand and experience this, imagine doing a hanging pull-up. Your arms are in tension when your body weight is hanging from the bar above. On a suspension bridge, for example, the beautiful Golden Gate here, the main cable, the catenary hanging between the two columns, is in continuous tension across the whole member. And then the shorter cables that are the hanger cables are in tension from that picking up the roadway to the main cable above. Members in tension fail by elongating to the point where they actually snap, as you can see in the member here. The release of tension of energy when an item snaps can be catastrophically worse than even just the structural failure. If you've ever over tightened a guitar string and popped it, you know what damage a cut wire can produce. The next condition I would like us to consider is the power of leverage, which is the magnification of force by application of it at a distance from a pivot point. This creates an exponential increase in force. As Archimedes said, give me a lever arm long enough and a fulcrum strong enough and I can move the world. I say exponential because in most cases the structural engineering equations multiply the load or force by the square of the distance involved, so that the length becomes a critical determinant of the size of a given member. To get a physical sense of the power of leverage, I just want you to imagine sticking your fingers into the working end of that pair of pliers and squeezing the other side. Or think about the power of your own bite strength, which is determined by the muscles acting against the pivot point of your TM joint of your jaw. Now, with the concepts of compression, tension, and leverage under our belts, we're ready to contemplate the first step typically taken in designing an actual architectural structure, which is to design the beams to resist the bending forces on them. Bending forces, or as it's termed in an engineering sense as bending moment, are created by the application of load on the lever arm of the length of the beam against the pivot points of the ends, pointer points. To get a physical sense of this, consider our athlete model doing a plank here, and when you feel this, the strain in your lower back and your abdomens resisting the bending of your body under the weight of yourself. The diagrams on the upper left show 3 instances out of the dozens that exist of the calculations that we use to determine the maximum bending moment for a given situation. Different loading types, different end conditions on beams, different constraints on the ends of the beams. Let's look now at how the mechanics of bending operate on a beam, and then understanding that, how that helps us to design and choose an actual structural member for a given solution. If you look at the diagram in the upper right, you can clearly see, because of the exaggerated sagging, how applying a load to its top surface causes the beam to bend in a downward curve, and because the radius then of the top of the surface is shorter than the radius of the downward portion, the top is shorter in length than it started off, so it's consequently squeezed. In other words, it's compressed, while the bottom is longer than what it started off as, and it's being pulled apart and isn't stretched in tension. The dotted line in the center of the beam is called the neutral axis because that's the original length of the beam, and consequently it's unchanged and is not under any stress. What this means for us in actuality is that the top surface and the bottom surface, bottom part of the beam, top part of the beam, are doing the most of the work, working their way down to the center where they're doing no work. The classic I-beam profile in the diagram on the lower right demonstrates the structural answer to this issue, which is putting the mass of the beam, most of the mass, in the outer flanges, the top flange in compression, the bottom flange in tension, and they're just tied together by a very narrow web that's just making them operate together to resist the bending. Here, leverage comes into play again, in that if you consider the web of the beam to be a lever arm with the 2 forces being applied at the ends, in other words, the top and bottom pivoting about the center point of the neutral axis, you can see that the deeper the beam is, in other words, the further apart the top and bottom are spread from each other, the greater will be its ability to resist bending. You can experience a visceral sense of what I'm talking about here by looking at the 2 images of the 2x4. If you imagine that you bought an 8-foot 2x4 and laid it on 2 separate sawhorses across from each other, laying flat, and sat on it, it's going to sag considerably. Whereas if you put it in standing vertically, it'll act like a horizontal bar beam. You could dance on it. The ability of a given sectional shape to resist bending, the principal determinant of that is called the section modulus. It's easy to determine for a rectangular section. It's just the width times the height squared. But for all other shapes, it actually gets fairly complicated. And it's the one time that I used the calculus I learned in my first year in school, in the second year when we determined the values of the section moduli of various construction shapes. Never used it again. Don't remember how to do it. I just know that it worked, and that's why I trust the values that are published for any given shape. All structural members deform when under load. They have to, even if infinitesimally. But they are also elastic. In other words, they will return to their original shape when the load is removed up to a given point. However, if overloaded to the point beyond their elastic range, they will permanently deform, and in that case they've failed in bending. So while our first level of consideration is designing a beam not to fail in bending, we also have to consider the commodity aspect of structural design as well. If we've loaded our floor joist, for example, to the point where a marble rolls to the center of the span, or the floor bounces as we move loads across it, the users will be uncomfortable and our design fails functionally. So the second step in beam design is to check the selection for deflection, in other words, the amount of sag. This is even a more complicated set of equations than determining bending abilities. But suffice to say that, again, leverage is the most important factor. In other words, while the load is a single determinant, the length of the beam is factored in 4 times, not multiplied by 4, but raised to the 4th power. Typically, building codes allow for a maximum deflection of 1/200th of the span. However, as seen in the image on the upper right, plaster and sheetrock ceilings will crack at that amount of movement. So typically, the design goal is nearly half that. The last step before our finalizing the selection of a beam is to check it for shear. Shear stresses are caused by the weight, the load on the beam, tending to slice it off against the edge of the bearing ends on either side. To get a sense of what this feels like, look at the model there or lean yourself on an edge, and that pressure against the side of your arm, the underside of your arm against the railing, is shear, or slicing the onion with a knife is caused by shear. Typically, beams that are of a moderate to long length don't ever have a problem with shear if they're adequately designed to accomplish bending, and it's kind of like an upsetting thing to get to the final point and then it fails in shear. So rather than changing the section that we're using and going to something more than what we need for bending or deflection, we'll typically just boost up the amount of material at the ends of the beams to increase its shear capacity. Where shear is the determinant is on short members, for instance, like the bracket that we're seeing in the upper left, where that is designed to work in shear first. It's not really going to be in bending. It's going to get sliced off if a load is applied to it. I think we may have hit a saturation point. I admit that I've been using my wife as a guinea pig, and I think the last couple of slides she's reached the bending maximum where she's going to deform. She's deflected as much as we're going to do. So why don't we at this point just step back and appreciate the glory of structural engineering, experience the joy of the Brooklyn Bridge. When I say joy, I'm recommending a hike across it at some point on a beautiful day. There's nothing like it. Coming back, particularly towards Manhattan and seeing that skyline, it's just glorious. I'll make one other recommendation also, which is David McCulloch's book. It's old. I realize it came out when I was still in school, but its description of John Roebling's efforts and his son Washington's to get the building completed, the building of the bridge completed, is fantastic. And given that this is a geography course, maybe we can consider also the impact of the Brooklyn Bridge. Certainly, Greater New York City, as it's termed, not officially, but the 5 boroughs wouldn't have occurred when it did in 1898 if this bridge hadn't been completed in 1883. It still would have been separate cities. The other 3 boroughs wouldn't have joined the Bronx and Manhattan in the city. One more geographic diversion before we delve back into the depths of structural engineering. Over 2 millennia ago, the location of the city of London was determined by the Romans when they founded the city at the westernmost point along the length of the Thames River, that their engineering allowed them to bridge across the river and have a port that ships could come up and navigate to. Though the bridge has been replaced numerous times since, it's always within the width of the roadway that it's gone back and forth and is still the center of the city to this day. Isn't that cool? This beautiful image of the bridge that was there in the 17th century, I think this is the one that was falling down in the child's nursery rhyme, is actually here in New Haven in the Yale Center for British Art. Hopefully we're mentally reinvigorated, and now let us return to our topic of architectural firmness and study the forces that cause the building stresses we've already considered. Irregardless of the Einsteinian question of whether or not gravity is actually a force, on our Newtonian planet that we architects work on, it's the principal force that we design building structures to resist. We categorize gravity loads as being either dead loads, the weight of the structure itself, or live loads superimposed on the structure, for example, people, furnishings, equipment, snow and ponded water on roofs. The photo illustrates and gives an example, for example, that the weight of the piano movers themselves is the dead load, while the piano they're struggling to lift is the live load. While the structures themselves don't differentiate and have to carry the combined weight of themselves and the loads we superimpose, architects and building codes make the distinction in order to aid in determining the total design load. We typically begin calculating by using the code-mandated minimum live load tables that specify, for example, that in a residential space, living spaces will have a uniformly distributed load of 40 pounds per square foot. Or another example would be a public corridor needs to carry 100 pounds per square foot. And then we add in a factor for the dead load. And finally, we will superimpose any special point loads, for example, heavy pieces of equipment, heavily loaded files or bookcases, or especially any loads that didn't align with this column grid above and are superimposed onto this floor that we have to carry with this structure. One of the principal live loads we have to design for has a distinct geographic component to it, which is snow loads. Obviously, if you're designing in Florida or Arizona, typically does not come into play. Whereas, as this map of Connecticut shows, we have to account for between a 30 and 40 pound live load for snow. The diagram in the upper left shows how this is actually just the uniformly distributed load. We have to account also for drifting loads that can vastly increase the amount of weight that the structure has to carry. As a personal anecdote, I'll mention that my daughter actually made the front page of the New York Times about 10 years ago or so when the building on Main Street, Middletown, collapsed, 4-story building, under a snow load and the heavy ice that we were having. Fortunately, the fire department was adjacent, and they heard the creaking and got everybody out of the building before the collapse. Having a building structure that's designed to stand up under its own weight, plus the gravity live loads that are superimposed, we next have to consider the lateral live loads on the building. Principally, these are wind and seismic forces that have a decided geographic element. This map of Connecticut shows how the wind speeds that need to be accounted for vary across the state. The shoreline particularly requires that building components are capable of resisting projectiles flying in hurricanes. The diagram on the left illustrates that wind loads are complex in their impact because they gust in different directions and even when sustained, cause pushes, pulls, and lifts in multiple ways. The insurance industry is even more stringent than building codes on these loads, and frequently public buildings will require that insurance companies approve the designs and installations of building enclosure materials, the roofing and siding materials. Historically, seismic forces weren't considered a major impact on the eastern United States. In fact, California required that architects seeking reciprocity from the rest of the country had to take an extra exam in lateral loads. However, that changed throughout the rest of the country in 1995 when there was a major earthquake in eastern Siberia in a seismic zone very similar to the eastern United States. And consequently, building codes changed, were updated, and practice and education for architects exponentially increased into our awareness of seismic loads. Hang in with me. I promise this is our last type of forces that act on buildings that we're going to consider today. I'm grouping several conditions that operate in different ways under the umbrella of chemical loads. The first being that matter in general expands when heated and contracts when cooled. Buildings need to accommodate this thermal expansion by allowing elements to move without tearing apart the building exterior. This can be particularly exacerbated when adjacent materials have different coefficients of expansion. For instance, aluminum grows much more quickly than brick masonry does, and if you had large sections of them that were tied together, they would tear apart. Instead, you need to be able to design them so that they'll slip past each other. The image at the top shows a concrete sidewalk that is buckled because it didn't have room to expand in length. The lower images shows a detail section of an expansion joint designed for paving. And as it demonstrates, these details can get fairly complex to accommodate movement in more than one direction and in multiple layers of the building at the same time. The one and only exception to the thermal expansion of materials in the universe is that water expands when going from a liquid to a solid state. At all other temperatures, it expands and heats as it heats like normal materials. But in this one case, the rule is turned on its head. This is why an ice cube floats in your drink. Liquid water is less dense than solid water. The expansive force of water freezing is incredible and creates significant stresses if allowed to happen within building materials. A significant amplification of this problem occurs in spring with the freeze-thaw cycle, as illustrated by the crumbling rock in the upper left image. If water gets into a fissure in the rock and freezes, it will expand the crack. And then if during a warm day it thaws, it will refill the now wider crack at a lower point, and when it refreezes, it expands the crack again and ratchets the action each time it freeze-thaws till it crumbles. The brick wall in the lower right is in the middle of this crumbling process. The architectural solution is preventative. We must design building envelopes to shed water and keep dry internally so that ice doesn't form within structures. Another case of the intense power of material expansion is rust jacking. As ferrous metals rust, they expand significantly. As illustrated in the two right-hand images, a rusting steel lintel designed to carry a brick veneer can actually push the veneer right off the building. The top left image illustrates the other most common situation, where concrete will spall off the face of a structural member if its steel reinforcing rusts. In both cases, again, the solution is preventative, preventing water from getting into the situation by coating the steel appropriately with epoxy coatings or galvanic coatings, and especially by preventing water from getting in ever in the first place. In the terms of the concrete, it's to have an adequate concrete cover of at least 2 inches for the reinforcing. And lastly and finally, a local example with decided geographic aspects is the crumbling foundation epidemic of northeastern Connecticut and southwestern Massachusetts. Over 35,000 homeowners in a 20-mile radius of Stafford Springs are potentially waiting for their concrete foundations to fail. This happened because beginning in 1983, a concrete batching plant there mixed in a naturally occurring aggregate that contained iron sulfides, it's called pyrrhotite, into their concrete mixes. They stopped using the contaminated quarry in 2015 when they discovered the problem. The mineral causes a slow deterioration of the concrete due to oxidation expansion when exposed to oxygen and water. It sometimes takes up to 30 years to begin the process, so this is unfortunately a continuing issue in the region. A sad example of not better living through modern chemistry. While individual structural members are designed in isolation to resist the gravity or lateral loads they each bear, their reactions are cumulatively passed on to subsequent, usually the lower units. But the architect's overall goal is to design a structurally stable building as a total system. This can be a challenge with terrabiated structures, particularly with simply supported beams. In other words, where the beams rest on columns or other supports and are unrestrained horizontally. One of the principal solutions is to use rigid joints in places, but these can be tricky and they're expensive, and in many cases they are complex. We won't get into the complexity of the numerous varieties of joints and bearing conditions that we have to design for. Instead, we can look at this image and absorb a clear lesson of what it's showing. I'd like you to come away with the overall encompassing concept that rectangular frames are inherently unstable and that they will easily rack into trapezoids because they can rotate about their corners without any resistance from the strength of the four sides, with only the rigidity of the joints holding them square. Whereas a triangular frame is inherently stable. The overall shape cannot deform without deforming the sides. This overall concept is in operation at all scales from micro to macro. In other words, stiffening a structure at any scale involves adding triangular braces. Making a joint rigid is in effect adding a triangular bracing element at the scale of the joint. Making a stable picnic table, adding cross bracing to the structural frame of a skyscraper all work because of the same principle at work. Bracing can be ad hoc and clumsy or elegantly done to achieve architecture with a capital A, as we're seeing here on the right. Mario Salvadori was a famous structural engineer, famous particularly in architectural circles, who wrote the book on structural design for architects. In fact, it's called Structural Design in Architecture. Mario was a close friend of my own mentor, Giorgio Cavalieri, so when he wrote another book in the 90s, I was reading it once when a client walked in, and the title of the book was Why Buildings Fall Down. I remember the client saying, "Did I hire the wrong guy?" Actual catastrophic structural failures are rare occurrences and most often occur from the amplification of stresses due to factors unanticipated at the time of design. Whether it's the collapse of the Mianus Bridge from rusting shear bolts caused by the intentional blocking of roadway drains during maintenance, or cascading pancaking of floor structures as occurred at L'Ambiance Plaza, giving two examples from here in Connecticut, architects and engineers react pretty quickly to tragedies. As we saw with the example of the Russian earthquake, code changes and practice changes follow on very soon. This image of the Tacoma Narrows Bridge is an example of an iconic failure taught to every student of structural design. Galloping Gertie, as she was nicknamed, collapsed because of the amplification of sway caused by the resonance of the structure with the prevailing winds. You know how this works yourself by just knowing the pendulum action of swinging a kid on the swing, how you can get him to go further and further with minimal input by doing it in the period of the time of the swing of the pendulum. Suffice it to say that suspension bridges are all designed with dampers to prevent this from happening anymore. Just as the FDA allows a certain amount of insect parts into our Cheerios, we don't expect structural materials to be perfect. In other words, imperfections in man-made steel or concrete and natural variations in wood and stone have to be accounted for in setting their minimum structural values. Also, given the unpredictability of human uses and abuses of structures, this leads us to add in redundancy to our designs and factors of safety of usually 3 to 4 or 5 times depending on the situation. While failures still do occur, one of the reasons they're very rare is because of these added precautions. At this point, maybe we can recap our survey of statics and basic structural design, and let's walk through the process of designing a typical frame structure. We first determine the live loads, and we'll be asking the structure to bear, and then add on the dead load value for the structure itself. We'll calculate the maximum bending moment these loads will impose on our joists and beams, and select members capable of resisting those bending forces. Check those selections to make sure they don't deflect too much and cracking ceilings or making occupants seasick, and then check they won't shear off at the bending ends. We'll next distribute those loads to the vertical members and select column sizes that work for the allowable compressive stresses, and then check their slenderness ratio to prevent them from buckling under the loads. Then we repeat the whole process at 90 degrees, calculating and checking the structure's ability to resist lateral forces, and add in bracing to assure the overall design stability. Finally, we'll consider the appropriateness of the factors of safety used and make elements more robust to increase maintainability or longevity as needs be, or as in our professional opinion we deem appropriate. Well, we made it. That completes our overview of statics and basic structural design, and I think we've earned a second bridge respite, and that we might enjoy examples of bridges specifically designed by architects. This first grouping are 3 of the dozens of bridges that Calvert Vaux designed as part of his design for Central Park. Vaux was the architect design partner in Olmsted and Vaux, the designers of the winning Greensward plan. And as you can see, his designs for the bridges were widely varied. The Bow Bridge on the lower right is one of the most elegant and beautiful arched bridges probably in the world. This next grouping are 2 of the bridges and a detail from a third of the 69 bridges that architect George Dunkelberger, a member of AIA Connecticut, designed on the Merritt Parkway that are major contributors to the fact that the Merritt Parkway is a national landmark. We'll conclude our bridge tour with 4 examples from Santiago Calatrava, an architect of my generation from Barcelona. I admit myself to a personal, certain iconoclastic bias. I sort of follow the Yogi Berra maxim of nobody goes there anymore, it's too crowded. And that if it's too popular, what makes it so special? So many works of most so-called starchitects leave me kind of in a kind of emperor's clothes kind of a way. But I am a big fan of Calatrava's projects. His work always impresses me as purposeful, clear, and elegant. He's had a bit of a backlash lately because many of his structures have been coming in over budget. Not that many other media darlings have held to that standard, but it is indisputable that his bridge designs, starting in the 90s, sparked a worldwide frenzy for cable-stayed and other exotic bridges, which I think is great. Everyone has to have a signature span now. Look at our own Q Bridge in New Haven as a wonderful example. In retrospect, I think I might have been a bit ambitious in the outline I put together in the introduction today. I think at this point we've probably had enough firmness for a week to digest. So I'm going to pull the sections on concrete and foundations, and we'll get to that next week. So from here on out, we'll have a few examples of concrete structures, but just looking at them in advance of our studies of the material itself and enjoy what it can accomplish. The Pantheon is probably, in my opinion, certainly is the greatest building treasure to come down to us from antiquity. Somehow, though, the temple front just hasn't thrilled me the way I would expect a landmark of this stature and age would. Now, who the hell am I to say? I don't, but it just seems a bit clunky, and I think that's largely because the building originally sat on a substantial plinth that it would have improved the proportions, but the ground plane has risen over the years due to repaving constantly over 2,000 years, 2 millennia worth of debris. Another reason the temple front is less impressive is that it faces north. Consequently, the lack of light and shadow contrast flattens out the composition. Whenever I've visited, it looks like this image. The money shot on the first slide was probably taken at some magical photographic golden hour I've always missed. The 2,000-year-old graphics still work, though, and you can't miss the signage proclaiming that Marcus Agrippa made this. But he actually didn't. He built an earlier version of the Pantheon during Augustus's reign that burnt down in a fire in 80 AD. When Hadrian had it rebuilt around 124, he recreated the inscription crediting Agrippa. But in that there is a cautionary tale for architects, in that the Arabian architect Apollodorus of Damascus, in all likelihood, actually designed this version. He'd been Trajan's favorite architect, Hadrian's predecessor, and was credited with popularizing vaults and domes. But unfortunately, Hadrian fancied himself an architect himself and took kind of umbrage at the credit going to Apollodorus and definitely had him exiled. It's said that he also had him killed, but that's more of a rumor. In any case, the warning to architects is don't overstay your welcome. As we said last week, when the project is done, the paint is, you're smelling it, it's time to move on to the next group of clients. Even the gargantuan scale of the 25-foot tall original bronze doors can't prepare you for the awesomeness that awaits you when you get inside, because when you enter, you have encountered perfection. In our second half today, we'll be looking into some of the proportional systems architects have used to help create the light with their designs. This is the original, simplest, and best, the proportion of 1 to 1 to 1. The ideal platonic solid of a sphere fits inside the Pantheon. The interior is just simply awe-inspiring, and always has been. Here's an image that really captures what it feels like to be in this space from 300 years ago, and it is the same today. Without any windows, The oculus provides the most incredible and beautiful natural daylight. While the Pantheon was completed a couple of generations after Vitruvius wrote, I can't think of a better model that epitomizes the integration of firmness, commodity, and delight. I mean, it's nearly 2,000 years old. The concrete structure is amazing. The interior is absolutely stunning. The lighting, everything about it, it's just, what can I say? Perfection has been achieved. And now we'll take our musical intermission with a piece that was written for and played with ambient sound in the Pantheon. We'll begin our consideration of commodity in architecture with a look at one of the more formalistic designs of our era, the gorgeous TWA terminal building by Eero Saarinen. While it may seem that the design was primarily concerned with its sculptural impact, it is a highly idiosyncratic design that clearly expresses its connection to flight. The tour de force concrete shell structure was very purposefully and elegantly tailored to fit its at the time new functions. I was a Cub Scout in 1962 when this opened, and we took the long trek out to Idlewild Airport, as JFK was known then, for a field trip from the Bronx to the outer reaches of Queens to watch the jets take off and get a taste of the state-of-the-art 60s cool futuristic life. And boy, did the TWA terminal provide that. It may not be the Pantheon, but it is another project that sets a standard that's hard to beat. Sadly, Saarinen died the year before the project opened from a brain tumor, but his short-lived practice was and is still renowned for finding elegant, purposeful, and very contextual solutions to their design projects. None of his buildings look like anything they designed before. In this case, the TWA terminal building was designed in the era when passengers still walked out onto the tarmac and climbed up a rolling staircase to board planes. Here, they created the concept of connecting a spidered hub for the gates that accessed the planes via some of the first jetways and tied back to the central head house via an at-grade corridor. The floor plan of the main level of the terminal is a model of clarity, with separated patterns for the movement of departing and arriving planes and passengers, their luggage, and ground transportation. It's so simple and elegant that it can be read as a graphic diagram of the solution to the problem. Happily, even though TWA is long gone, Saarinen's head house building for them here at JFK lives on. It's now a hotel as part of the JetBlue complex at JFK. As we discussed last week, architecture is defined as being structures that are occupied and used by people. As such, architecture can be sculptural, but sculpture isn't architecture. I've put together this slide to demonstrate some of the typical initial steps that architects go through in the process of designing a solution to their client's problem. They illustrate 4 stages of the programming phase of designing, in this case a hospital. Starting at the upper left is a spatial relationship matrix. It's a written list of the building program elements that have been organized by their adjacency requirements. For example, the operating rooms need to be adjacent to the recovery rooms, but separated from the utility loading docks. The next image is a bubble diagram that graphically represents this information so that the design team and clients can imagine where different functions will occur relative to each other. Sometimes this will be entirely generic when we're just beginning and idealized, and sometimes we will adapt it to the given site conditions, locating where the streets are, where pedestrians are coming from, where traffic comes from. Often we will generate the rule of 3 choices at this point and have 3 overall wide divergent options to pick from to begin with. The third image above that one then is a blocking plan where the same concepts are now regularized into rectangular or space-appropriate plan shapes that are accurately scaled to one another and located as they were determined to be in bubble diagrams. And then the final stage is a first pass at a schematic floor plan as we see on the right. The Starrett-Lehigh building in New York's historically industrial west side occupies a different end of the spectrum from some of the world landmark structures that we've been considering so far today. It's a background building and one of my favorites. I've always loved this building. It's very straightforward, very robust, very strong. Likewise, in terms of programming, it occupies a different end of the spectrum as well. It was designed and built to be a spec office building, essentially, warehouse office building. In other words, there was no defined program for the individual spaces. It was up to the tenants to fill them how they saw fit. Even though the building isn't asserting itself stylistically to stand out from the crowd, it does make the most aesthetically of its limited palette and budget. Straightforwardly, it expresses its concrete structural slabs at each level that carry the common red brick spandrels and industrial ribbon windows at each level. I love the structural honesty of this look, but unfortunately you couldn't recreate it today because the concrete slabs act as radiators from the inside of the building, and we call them heat sinks. This detail wouldn't meet even the minimum energy codes of today. The Starrett brothers were prosperous architects/builders who'd been very successful in designing skyscrapers. They partnered with the Lehigh Valley Railroad to develop the Starrett-Lehigh building for themselves. While, as I said, the individual tenancies weren't pre-programmed or planned for, the building design incorporated features that allowed for the flexible use of the large 120,000 square foot floor plates. They capitalized on the site's location. The elevated freight railroad came directly into the building at the second level, while trucks that entered at grade could deliver directly to any of the 19 floors via the massive freight elevators that you can see in the diagrammatic section to the left. It was a very ambitious project that filled the entire block between 11th and 12th Avenues and 26th to 27th Street. In other words, it's 600 feet long by 200 feet deep by 19 stories tall. They created over 2 million square feet of space to rent that unluckily came on the market during the Great Depression, and unfortunately for them had a hard time filling the space and was underutilized for generations. One detail I'd like you to look at in the photo to the right are the mushroom caps, as we call them, the straight flared capitals of the concrete columns. And as we learned earlier today, these are necessary for shear reinforcement because while the reinforced concrete flat slabs are adequate to take the large bending loads of a 200-pound per square foot industrial live load, the columns would have punched through those slabs if the load wasn't spread out over the larger diameter of the capitals. While the building's connection to the railroads was severed in the 60s, it's ironically the death of the rail service altogether and the creation of the High Line that was an impetus for the hipsterization of the overall area. And now the building is full, and as you can see, it's very stylish, currently occupied. Powers of 10 is a short film that the Office of Architects Charles Ray Eames produced in the 70s. It demonstrates how our perceptions alter as it focuses in and pans outward by order of magnitude steps from the human scale of our bodies down to the atomic and outward to the scale of the whole universe. Please take the 9 minutes that it takes to watch it. It's easily found on YouTube, and it's well worth the time spent. A lesson I take from this mental game for architects is that our designs exist in this same scale context, and to consider our decisions based on their impacts at a level above and down below the scale that we're working at. Not just physically, but conceptually as well. One issue that I often bring up is the idea of stepping back from the problem that's presented to us to solve and questioning, is it a problem at all? I have, and my firm has talked ourselves out of work at times, but the issue is we're professionals and we're taking the client's interest above ours. Today, we'll take our first look at delight as an area of conscious study by architects. We'll consider some of the mathematical proportional systems that architects use as design aids or after the fact for analysis. Some systems are quite straightforward, as we saw with the spherical ratio of the Pantheon being 1 to 1 to 1 in all three dimensions. Some are just simple numerical ratios that historically been deemed pleasing, and some are more arcane in their determination, but we've developed an eye to recognize when their bell is being rung correctly in tune, and it's kind of jarring when they're not. Returning to where we began today, we'll consider the Parthenon not in the concrete terms of statics and structure that we looked at earlier, but in the abstract as a geometric study. As we learned last week, architects think and design in a two-dimensional world of our orthographic projections. So these flattened out images of the temple front enable us to consider the underlying geometric thinking behind the design. In this case, two versions of the so-called golden section have been overlaid on top of the elevations to see how the temple correlates to that proportional system. I'm going to skip the mathematic and geometric derivations of the golden section or the golden ratio, which is approximately 1.618 to 1, because I find it very interesting, but I'm afraid I'll squeeze all the joy out of it in my explanation. So I'll just say that it's a proportion that we've found to be used frequently in nature. The spiral of a nautilus shell of cut in section follows the proportion and seems to align with points on the Parthenon as well, as that overlay shows. It also correlates with the proportions of our own bodies, as Vitruvius described and Leonardo illustrated for us. So it is a favorite of architects to consider and use frequently. While it seems the golden section may predate us as a species, the next system we'll consider is only a few millennia old and definitely human in origin. The classical language of the five orders is described by our very own Vitruvius and expanded upon by Renaissance scholar architects. The orders are in order, as seen in the right-hand image: the Tuscan, Doric, Ionic, Corinthian, and Composite. The proportions of this system are derived from the ratio of the module of one column diameter to its height, and they range from the Tuscan, which is 1 diameter, to 6 or 7 in height, to the Composite, which is 1 diameter and 10 in height. And as we saw in our first half today, consequently, the Tuscan is the strongest in resisting buckling, as its slenderness ratio is the highest, while the Composite is the wiggliest. Architecturally, this is recognized by the order in which they can be superimposed upon one another. In other words, a 5-story structure could appropriately have a Tuscan basement, followed by a Doric first floor, a second floor of Ionic, etc. While where all of the orders don't need to appear, you can have a building of Tuscan, 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 or just solely, a Doric with an Ionic on top of it. It would be a true faux pas to have one of the lower, heavier orders bearing on a story of lighter proportions. That cannot occur. The details of each order are also derived from the same proportions, and while there's obviously flexibility, they are codified to the extent that, for example, mixing a Doric entablature with a Corinthian column would seem jarring. And while a typical architect today doesn't study the five orders in depth as our Renaissance and Classical era forebears did, in the same obsessive ways that they did, the books that they created are still available for reference when the need arises. We call the use of the five orders the classic language of architecture because they have developed deeper cultural meanings. For example, traditionally the Ionic supposedly represented the slender maidens with their curved hair capitals are used in buildings that are more civilized programs. For example, libraries, courthouses, it's seen as appropriate to use the Ionic, while the Doric is seen as representing the martial attributes of the male figure. As an example, not being gender biased but being historically contextual, I designed a police headquarters addition to a nationally registered landmark town hall. The entrance to the town hall had an elliptical Ionic colonnade, which is appropriate for a general town hall use. And so we designed a squared-off Doric entrance for the police facility to represent their appropriately more martial attributes. Andrea Palladio, the 16th century Venetian architect, had a prolific and highly successful career. His designs for suburban and gentleman farmer agricultural villas, all located in a tiny quarter of the Veneto, are justifiably world-renowned. He was a serious scholar of Vitruvius and the classics, but his own new ideas on proportion disseminated via his illustrated 4 books on architecture made him possibly the most influential theorist since Vitruvius himself. On the right hand is a woodcut illustration of the plan of the Villa Baudor that's keyed to a legend describing a system for sizing interior rooms. Essentially, he used pleasing whole number ratios in section and plan based on a theory that musical harmonic proportions are pleasing in general. So squares and cubes as being 1-to-1 or the octave are great. 3-to-4, 2-to-3, 3-to-5. He didn't invent this thinking. It goes back to Plato, as we saw with the Pantheon, but he made it accessible to everyone. The image on the left of the 2 greater rooms of the villa show why his influence was and is so great. His system works. It works at creating beautiful spaces. Palladio's more public buildings were also inspirational in promoting the Renaissance of classicism as it supplanted medieval design throughout Europe. This design, the Basilica Palladiana at Vicenza, has been a model for numerous public buildings for over 4 centuries, but it's even more noteworthy for popularizing the Serlian motif, as cognoscenti architects term it, giving credit to Sebastiano Serlio, who first developed it, but it's more popularly known as the Palladian window. I often think of this building in my role as chairman of Middletown's Design Review and Preservation Board because it's a renovation of an earlier building by Domenico Vicenza. I tell applicants that we'd be happy if they propose to modify any of our historic structures, if they get Palladio to design it. Just look at this. I just wanted to give you a moment of silence to take in the clarity and the elegance of his thinking. This facade of the Villa Baudor is just sublime. This is why architects continue to obsess over his work. I have friends who regularly make the pilgrimage to visit the villas. I have a friend who had a very technical career in architecture, and he's obsessed with Palladio. He's gone and bought a villa, not a Palladian villa, but a villa in the area so that he can be there. He's even written a book on the topic. England in particular took a literal page from the 4 books of architecture, in that Inigo Jones, their first Renaissance architect, and whose lifespan just overlapped with Palladio's, was a devoted disciple, and kind of like Augustus in Rome, took a red brick Tudor country and introduced modernity in the form of limestone ashlar. His queen's house, built for the unfortunate Charles I's Danish queen, is the first classical building in England, and it's obvious looking at it that Inigo took his lessons in proportion to heart. This is a beautiful building and a landmark cherished to today. England's American colonies also followed suit in architectural thinking and fashion. Essentially, what we've later termed Georgian architecture in the U.S. and its earlier colonial high designs of the 16th century, as well as later style terms that were used through the early 19th century, early days of the Republic, were studious or simply fashionable copies of Palladio's text directly or his teachings through later copybooks. This is the Wren Building at William and Mary University in Virginia, and is attributed to be designed by Sir Christopher Wren himself, London's polymathic architect genius, friend of Isaac Newton. I'll close out our consideration of delight today with a personal observation and an appreciation of how architecture can just make us feel good. As I was putting together the slide deck for today, I looked up and realized I was under the subliminal influence of a direct Palladian history. I've restored the finishes in this room myself, and while the window sash that you're looking at and the plank flooring date from an 1830s renovation, the paneling and the proportions of the original are from 1765, when John Hall built this house in Middletown with probably a copybook of Palladio's. I'd also like to thank at this moment my assistant here, who's looking forlornly and studiously, but hasn't barked throughout the day as I've been recording. So thank you, Marco. For our assignment this coming week, we will be reading Chapter 2 of Experiencing Architecture, titled Solids and Cavities in Architecture. This chapter includes 2 buildings from Rasmussen's native Copenhagen that exemplified divergent approaches to creating and analyzing designs, either contemplating objects as being additive or subtractive. The 2 buildings are fairly contemporary, both being about 100 years old now. The police headquarters on the left is slightly newer and has been smoothed down to a refined elegance, while the City Hall exuberantly celebrates its civic functions with latent Victorian embellishments and additions onto it. I personally have a proclivity for the former, for the simplifying and editing, because that tends to be where my own skills are. But I love both types of buildings, and I love both of these buildings. For next week, please prepare a piece, possibly an assemblage or collage or a comparative study, for presentation to the class that enhances the composition by either adding detail or refining via editing. Now let's pin up your observations of the background buildings you saw on your architectural hikes. The class will review them by the lens of the new tools you've all acquired from that first chapter. As Rasmussen writes, details tell nothing essential about architecture, simply because the object of all good architecture is to create integrated wholes. Understanding architecture is not the same as being able to determine the style of a building by certain external features. You must experience it. You must observe how it was designed for a special purpose and how it was attuned to the entire concept and rhythm of a specific era. We'll conclude today's session with a case study of Joyner Health Sciences Center, a building I designed for the state of Connecticut at Northwest Community College in Winstead. We can use this as a kind of recap of the issues that we looked at today. Let's see if I can walk the walk, or is it all talk? To begin, let's take the lesson from the Eames Power of 10 and step back in order of magnitude and consider the historic and geographic context of the project. The beautiful neoclassical building on the right is the original 1895 home of the Gilbert School, which is a privately endowed public high school. It's similar to the format of Norwich Free Academy. The high school built a new expanded facility in the 50s, and so the state adaptively reused the building as Founders Hall for the new community college. So this is our campus role model for our design. Happily, my firm got to renovate Founders Hall and do a few other projects on the lovely campus that faces the town green, which is about a 3-minute walk from our site, which is shown starred at the intersection of Route 44 with the most northerly entrance of Route 8. In other words, the highway commences right here at our site and traffic whips right around it. The frightening image on the left shows the aftermath of the 1955 Mad River flood that wiped out half of Winstead following 2 successive hurricanes in a week. As we'll see, this has direct implications for our site. Initially, the state had come to us to design modifications to an existing structure on the site that had originally been built in the late 50s as a one-story supermarket. That was shown on this existing conditions survey and sitting on the southeast corner of the site. And unfortunately, it ended up being way too close to traffic when the entrance ramp for Route 8 sliced off a corner of the property. It was a nerve-wracking experience to walk into the entrance of the building with traffic zipping by. They actually had to have a guardrail up to protect you as you walked in. Northwest Community College had been using the building with minor alterations for a number of years. Unfortunately, the building was settling unevenly and had severe structural issues, while at the same time the basement space they'd been using for half of their program spaces was too low and didn't meet code habitability requirements. The late 50s construction date, and if you look on the left of the survey, the unnaturally straight, parallel, and very steep contour lines along the western side of the site gives us a clue as to the historic and geographic influences from our next order of magnitude that we saw on the last slide. When the Mad River wiped out half of downtown Winstead, they bulldozed the area to clear the debris, but it had to end up somewhere. This is where it ended up. So our site is composed of a pile of brick, stone, concrete rubble with a nice amalgam of 1950s Buicks and a Kelvin-era refrigerator or two. Not an ideal substrate for a building site. So we prepared a 70-page programming and planning study that pretty much almost talked us out of the project. But fortunately for us, the Department of Public Works came back to us to design a new building on the site that was engineered to accommodate the subsurface conditions. We studied 3 site concepts and agreed on this solution that locates the new building along the northern property line and is set back enough from Route 44, enough to create a pedestrian-friendly entry plaza at the front of the building, and is just a bit closer to the rest of campus. This location also allows us to complete the new structure before we had to demolish the existing building. And this saved the state several millions of dollars that they would have had to spend in temporary facilities rental and outfitting. And finally, as we'll see in the next slide, this was actually also the ideal structural location for our new building's foundations. This longitudinal section explains kind of an overall the concept of the building we designed. It's a rectangle with its long axis perpendicular to the steep slope of the site. I had intended to go over foundation design this week, so instead this preview will be a foreshadowing of our next session. The footings for the building needed to be deeper as they approached the western end and the steep slope of the site, so we capitalized on this to create a 2-story basement that then steps up to a 1-story section that finishes at midway. This extra headroom allowed us to house all the mechanicals in the basement, since ductwork, conduits, piping can all cross each other and still leave room for equipment and people beneath. It seems simple enough overall when we were done, but the building houses 2 related but distinct programs, veterinary and human health sciences. The classrooms for each program could have been intermingled, but the veterinary program has a clinic with exam rooms, kennels, x-ray facilities, and 2 operatories that ideally needed to be adjacent to the veterinary classrooms, but separated, particularly with a fully isolated ventilation system from the human program. Our solution was to stack the 2 classrooms into a single wing, with the 1-story wing for the veterinary clinic on the south side of the building. This allowed for a direct entrance by the public and their animals. They wouldn't have to traverse through the academic areas, and also allowed for the pets to have an adjacent outdoor space to run and relieve themselves. The second floor space has a single loaded corridor. In other words, it's able to have windows along the length of the corridor, and it's a very pleasant space for the students to mingle across. Interleaved in a kind of syncopated rhythm are a series of light scoops that then also bring natural daylight down into the double-loaded corridor of the first floor. It also lights the interior kennel spaces of the veterinary clinic. The last detail I'd like to point out is on the left-hand side, facing west, is a projecting balcony. It cantilevers out from the building so that there's a Juliet balcony essentially at the end of each corridor level, and you get a 360 degree or 270 degree view of this glorious view to the west. I did begin the building design with freehand sketches of elevations and plans, but pretty quickly did move into a three-dimensional digital model in which I sculpted the masses and elements of the building and hopefully refined the design, editing to remove superfluous detailing, leaving, I hope, a cohesive statement. I did massage the elements to align with the numeric proportions I chose. For example, the square vestibule projects off from the overall golden section of the lobby by a depth that is 2 golden rectangles in height. The end result should be subliminal, I hope, but a sense of the pleasing proportions come across. I do hope the students and faculty experience some pleasure as they enter the building from this plaza on the building's east side. The design team and our clients at the Department of Public Works and the School Facilities Unit invested a lot of effort and a good deal of the state's money into it. This view from the south entrance, driveway entrance, gives a pretty good overview of the whole disposition of the design. The Joyner Building is the first building that you'll see of the campus of Northwest Community College coming from the south up Route 44. And we did try to tie it back to the original historic portions of the campus by using the same materials palette that was on Founders Hall with the blonde brick and, in our case, a very nice cream terracotta that matches the stone of the original building. I'm also kind of proud of the carved terracotta signage that I designed for the corner of the building as well. This is a view looking up within the vestibule at the entrance. And here we're walking up the stairs in this lobby up to the second floor. This is an image from the ground floor corridor looking up into one of the light wells, one of the light scoops, bringing natural daylight down into the ground floor corridor. As you can see, they're lined with reflective aluminum panels to bring the maximum amount of light down as possible. As a reminder from last week, a project even of this simple enough scale, 2-story building, had a couple of hundred E-size drawings, thousands of pages of written specifications, and an overall design team of at least a couple dozen people, not to mention the contractors and client representatives. On a healthcare project such as this, we'll also have additional specialty consultants, medical planners, in this case a good friend of mine from my earlier career days in New York City consulted to us, a physicist to determine the amount of lead lining needed to shell the X-ray suite, and specialty HVAC consultants even to deal with medical gases and anesthetics besides being toxic or flammable. But the crux of the team were 3 architects from my office who worked directly with me and then supervised the efforts of everyone else. They were the project manager, who is now one of the partners leading our firm these days, who coordinated all of the interactions with the client and during construction with the builders as well. A job captain who coordinated the design team itself, including all of the consultants, and was responsible for the bulk of the construction detailing. And then finally an interiors planner who led the selection of all the finishes, lighting, furnishings, and the medical equipment as well. From my perspective, then, my role as the conductor of the orchestra, so to speak, was to provide a strong enough concept for the building overall that it carries through and can be experienced while still allowing for input and contributions from everyone else. I used to say I don't care where the best idea comes from as long as we use the best idea when I was describing it to clients. In this case, the interiors folks went an extra mile or two in designing custom tile patterns for the restrooms, and I think while they had some fun, hopefully the people using the facilities do as well. Sometimes they'll get a little whimsical and leave their fingerprint, in this case paw prints. If you look at the ceiling, the interiors architects found some custom tiles that have animal footprints on the ceiling in the veterinary waiting room. Here's the exterior projection of the Juliet balconies on the west side of the building. And finally, you get to be Juliet and stand here on the ground floor looking out over the beautiful vista really to the west, looking across the Mad River Valley. And I'll wrap up with this view from the second floor, looking out across again a little bit more of the view because you're that much taller. And see you next week. And I'll wrap up with this view